Hey, what's up, guys? Dr. Stotts here. We're going to keep on rolling with our stoichiometry stuff. And we've reached the point now where we've been adding layers every week. And we're now to the point to where we can do some really kind of some full-blown stoichiometry. And what we've been doing is stoichiometry, but now we're getting to where we are actually comparing quantities with other quantities in the reaction. And that's my first point, is just a reminder about what stoichiometry is. And get that color away from there. Stoichiometry is relating one quantity that's in a reaction to another. So we have a reactant that maybe we are relating to a product, or sometimes even a reactant to another reactant, and vice versa. And if you remember last week, we were doing that with our mole ratios. We were showing all those different relationships that we have in the within a reaction. I want to make this next point, and I want to come back to it as we get into some of our practice problems. So here's this point. If you are relating different substances one to another, like we do in stoichiometry, then one of the calculation steps must relate moles of one substance to moles of another substance. Okay, so let me say that again. When we're doing these problems, if we are relating, say, grams of oxygen to grams of carbon dioxide, we can't just go from grams of one to grams to the other. We've got to find a middle ground, and we do that by relating. We convert both of them to moles and then relate that number of moles to each other. And that's what we did last week. That's the mole ratio that we obtained from the balanced equation. So I'm going to come back and mention that point as we do some of these practice problems. So I've got 3 practice problems lined up here that closely mirror your practice that you're going to do for this week. Okay, so let's just jump right in. Now, I've been a good guy, and I've given you the full balanced equation. I'm trying to cut as many corners as I can for you guys right now. If we were, in a normal situation, I would give you word problems, and you would have to translate those words into these chemical equations, and then balance the equations and all that. So I'm giving you a break. So I'm trying to be good. So let's read what we got here. We've got our balanced equation up here, and that equation is iron oxide, Fe2O3, is reacting with hydrogen gas, and it produces iron and water. Okay? Anybody know what kind of reaction that is? Bonus points if you tell me on Teams. Okay? So now let's read the actual problem itself. Calculate how many grams of iron. So right off the bat, that's what we're trying to find. We're trying to find grams of iron. How many grams of iron can be made from 3.7 moles of Fe2O3 in the reaction above? So we're trying to calculate how many grams of this will be produced if we have 3.7 moles of this. Okay, so here's how that looks in your crossbar. Exactly the way that we've been doing all of these. Okay, I want to give myself plenty of room because these are going to have multiple steps. Okay, what were we given in the problem? We already stated that it was 3.7 moles of iron 2 oxide. I'm sorry, iron 3 oxide, Fe2O3. All right, and we are asked to find grams of iron. All right, so we are in moles of one particular substance, and we're asked to find grams of another. Now, there's not just a single step that will take us from moles of one to grams of another. Okay, now if you get into the problem and you have absolutely no idea what to do, remember that we are going to have to cancel diagonally here. We're trying to move away from this unit. So what we're going to do, we're going to put moles of Fe2O3 on the bottom. Now the question comes in, what do we put on top? Well, grams of iron is our end goal. That's what we're trying to get to. But we can't just put grams of iron up here because we don't have a conversion that takes us from moles of iron oxide to grams of iron. We don't have a relationship for that. However, we do have a relationship like our mole ratios that we talked about last week that tells us, if you look back at your balanced equation, for every 2 moles of iron we have, that corresponds with 1 mole of Fe2O3. Okay? 2 moles of iron for every 1 mole of Fe2O3. Now, that mole ratio is extremely important because that mole ratio, this is the step that I was referring to with this point here. Because this step, it's kind of the bridge between both of these substances. It's the bridge between Fe2O3 and iron. And that's how we relate one substance to another, is getting them both into moles and then seeing what that relationship is between those two. And we get that relationship again from the balanced equation, our mole ratio. Okay, so now if I were to stop the problem right here, moles of Fe2O3 cancels with moles of Fe2O3. And I am now in moles of Fe. I'm in that unit. Now, I don't need to stay there. Remember, what's my end goal? I'm trying to get to grams of iron. Okay, so right now, moles of iron is what I want to cancel. And I'm trying to get to grams of iron. Now, here's a step where we know how to do this. This is molar mass. 1 mole of iron for every how many grams of iron? Let's pull up the periodic table here. 1 mole of iron is 55.85 grams. 55.85 grams. All right, so now moles of iron cancels, moles of iron cancels. We are now in the unit that we need. So now it's just math. 3.7 times 2 times 55.85. All right, let's crunch that over here. 3.7 times 2 times 55.85. That gives us 413.29. Okay. So now, what does that tell us? That tells us that if we have a reaction and we have this much iron oxide as a reactant here, then we're going to produce this much iron in that reaction. And that's stoichiometry. Okay, we've related the quantity of one substance in the reaction to another substance in the reaction. Okay. Now, I want to point out that this particular problem, notice, let me point out that we went from moles of one substance to grams of a different substance. Now, every problem will be different. Sometimes you might go from moles to moles, okay? In which case, we wouldn't have had to do this molar mass step here. Sometimes you might have been given grams of Fe2O3, and your first step would have been converting those grams to moles of Fe2O3. So you just got to work with what the problem is asking, okay? And I've given you a couple different looks at it in these examples here. So now here's one where we're going to go from grams of one to grams of the other. So this is going to be a long crossbar. So again, I've given you the balanced equation. Let's read the setup. It says how many grams of oxygen are needed, so we're trying to find grams of oxygen here, to produce 56 grams of nitrogen monoxide. So there's nitrogen monoxide. So if we want to produce 56 grams of this substance, how many grams of oxygen do we need to start with? Okay, crossbar. Like always, what was given to us? The problem told us that we want to produce 56 grams of nitrogen monoxide. No. And what are we trying to find? Well, we're trying to find how many grams of O2. Now, it is O2. Remember, it's not just O. Oxygen is diatomic. How many grams of oxygen are we going to need to put in this reaction to produce this much? Okay. So now we start mapping this thing out. We are in grams of nitrogen oxide to begin with. So we know that we want to move away from grams of nitrogen oxide. So we put it on the bottom. Well, what do we put on top? Well, remember that I said that in every one of these stoichiometry problems, we're going to have to get to a step where we're relating moles of one substance to moles of the other substance. So this first step here, we're going to convert grams to moles. So we're going to go from grams of nitrogen oxide to moles of nitrogen monoxide. All right, and that's just the molar mass. So 1 mole of nitrogen oxide equals how many grams? Well, I'm going to come off to the side and say, all right, I've got 1 atom of nitrogen there, and that's 14.01. I've got 1 atom of oxygen, and that's about 16. So I'm looking at about 30.01 grams. Okay, so now I cancel my grams of nitrogen oxide, and now, or monoxide, sorry, I keep doing that. And now I'm in moles of nitrogen monoxide. And that's a good thing, because this next step is when I'm going to convert moles of the first substance to moles of the substance that I'm moving toward. Moles of O2. Now, let me make that a little bigger. Now, where do I get this information? Moles of O2 to moles of NO. Where do I get the numbers for that relationship? I'm sure somebody said it. I hope you did. From the balanced equation. So notice our mole ratio from the balanced equation says that for every 5 moles of oxygen, of O2, and remember, it's O2, include that too, for every 5 moles of that, we produce 4 moles of NO, okay? So there's our relationship there that we use. So now we keep going here. Moles of nitrogen monoxide cancel with moles of nitrogen monoxide, and we are now in moles of O2. Okay, we're getting close. We need grams of O2. So now I want this moles of O2 to cancel. So I put it on the bottom, and I'm trying to get to grams of O2. All right. Now here's where you gotta be really careful, because I want to make a point. I keep throwing out this fact that this is O2. So this is, we use the molar mass here, 1 mole of O2. How many grams of O2 is in 1 mole? Well, oxygen has a mass of about 16, but this is O2. So O2 has a mass of about 32 grams per mole, okay? So don't forget that diatomic aspect of oxygen. So now moles of O2 cancel, and it's a math problem. And let's make sure that we do this order of operations correctly, because we multiply all the way across here. 56 times 5 times 32, and that's over 30.01 times 4. So crunch those numbers on top. Let's see what we get. 56 times 5 times 32. I got 8,960 on top, and then multiply across the bottom. 30.01 times 4, 120.4. So now we divide the top by the bottom. So 8,960 divided by 120.4, and I got about 74.4 grams. Okay, so what does that tell me? That tells me that if I want to produce 56 grams of nitrogen monoxide as a product here, I'm going to need to start with 74.4 grams of oxygen at least. Okay. Looks pretty hairy, right? But the math it's just multiplication and division. But you got to get your setup. Now, I want to point out, remember I kept stressing to you guys, make sure that you write down as much information as you can, and make sure that you show me that you're canceling things. And hopefully now, in a setup like this, you can see how important that is, because if you didn't write like O2 or NO, you wouldn't know, what compound you were working with. Okay. All right. Last example here, and look at that equation. It looks hairy, right? But we do it exactly the same way. So we've got how many grams of sodium sulfate. Now this is sodium sulfate down here, sodium sulfate. How many grams of that, so grams is what we're looking for, will be formed if you start with 200 grams of sodium hydroxide. So if we start with 200 grams of this, how many grams of that will be produced? So big crossbar, give yourself plenty of room. What are we given? We're given 200 grams of sodium hydroxide. What are we asked to find? We need grams of Na2SO4, sodium sulfate. Okay, so now we start our journey. We are in grams of sodium hydroxide, so we know that initially we want to get away from that unit, so we're going to put it down here so it'll cancel. And remember, one of these steps, we've got to get to a step where we're converting moles of what we started with to moles of what we're moving toward. So in this first step here, we're going from grams to moles. And you will hear that in almost every chemistry problem in college chemistry. Convert to moles, convert to moles. So in all of these, guess what? That's our first step. We're converting grams to moles. So grams of sodium hydroxide to moles of sodium hydroxide. Okay, so 1 mole of sodium hydroxide equals how many grams? Well, where do we get that? That's a molar mass. We've got to calculate that. So come off to the side and see, all right, I've got 1 atom of sodium. That's 22.99. I just remember that. 1 atom of oxygen, that's 16. 1 atom of hydrogen, which is 1.01. So I'm going to add those up really quickly. 22.99 plus 16 plus 1. And that comes to 40 grams. So 1 mole of sodium hydroxide is 40 grams. Okay, so now grams of sodium hydroxide cancel with grams of sodium hydroxide. This next step here is where we're going to do our mole-to-mole relationship. So I've got moles of sodium hydroxide on top here, so I'm going to put it down here on the bottom so it'll cancel. All right, moles of sodium hydroxide on the bottom, and I'm moving toward sodium sulfate. So I'm going to relate this to sodium sulfate. Now, what is the numerical relationship between those two compounds, and where do I find that? Ding, 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 from the from the balanced equation. So remember our mole ratio stuff from last week. So how many moles of sodium hydroxide relate to moles of sodium sulfate? Well, there's 2 moles of sodium hydroxide, and that relates to, there's just 1 mole of sodium sulfate. Okay, so now moles of sodium hydroxide will cancel with moles of sodium hydroxide. If I stop the problem right there and I did this math, 200 divided by 40 times 2, that would give me an answer in moles of sodium sulfate. Okay, because all my other units are canceled. But I need to keep going because the problem asks me for grams of sodium sulfate. So I need one more step here where I convert moles of sodium sulfate to grams of sodium sulfate. Okay, so now I total up my molar mass here. So 1 mole of that compound, and I've done this on the side already over here. Save a little bit of time. 142.04 grams. So I just added up my molar mass there. So now moles of sodium sulfate cancel with moles of sodium sulfate, and now it's a math problem. I multiply across the top, so I've got 200 times 142.04 divided by what's on the bottom, 40 times 2. So on top, 200 times 142.04 equals, I got 28,408, and then divided by 40 times 2 on the bottom, which is 80. And that gives me 355.1 grams of sodium sulfate. All right, so that's the 3 example problems. I can't stress enough, guys, on this stuff. You need to reach out to me if you run into the first question. It doesn't take 5 minutes to pull up a Teams chat and share my screen and work the problem and fix any issues that you might be struggling with. And also, I can't stress enough that I need to see your work on this. I've got to see your work with a crossbar, and some of you were doing it and you didn't use the crossbar, and that's fine. But here's the thing: I've got to see your processes. I've got to see your calculations, because I can put this formula into Google and just put in 200 grams of sodium hydroxide equals how many grams of sodium sulfate, and it's going to spit out an answer. I can give you the answers, and that's not what I'm assessing. I'm assessing your ability to, go back to the very first slide here, to relate one quantity to another. And the way that I do that is seeing that you understand these relationships and how they relate to one substance to another. Okay. So hope you guys have a great week. I miss you guys. We're wrapping it up. We've got one more go at this next week. I'm going to give you some problems that it's not going to be a traditional assessment. I don't want to do that, but it's going to be some problems that kind of pull all of our concepts together, where you may have to translate some words into an equation and balances and do some of the stoichiometry stuff. So we'll see what that looks like. Okay. All right. You guys have a good evening and good week. Be safe, and I'll see you guys.